The voltage in your home might be rising and the cause could be next door. More solar panels, more batteries, more EV chargers, all pushing and pulling on the local grid. Most people will never notice. But for EV drivers, one clause buried in the wiring regulations can turn a harmless looking voltage rise into a charger that simply refuses to play. Grid operators have suggested a controversial quick fix, but parts of the industry are fighting back. Is it a practical solution or just a sticking plaster on an already strained network? To answer that, we first need to look at what's causing the problem. For most of its life, the electricity grid was a one-way street. Power was generated in big central power stations, stepped up for transmission, stepped down through substations, and finally pushed out along local streets to homes and businesses. It was top-down, predictable, and, compared with today, beautifully well behaved. Demand was so predictable that generation could even be planned around TV schedules. If millions of people were about to put the kettle on after a program finished, the system had to be ready. That predictability also made voltage easier to manage. In our year 2000 street, the transformer sits at the start of the feeder and the power flows away from it. The homes closest to the transformer generally see the highest voltage. As you move further down the street, each house takes a little more power, the cable loses a little more voltage, and the homes at the far end see the lowest voltage. That was not a fault. That was the expected shape of the network, a gentle electrical downhill slope, but that slope has to stay inside a legal envelope. Under the Electricity Safety, Quality and Continuity Regulations, or ESQCR, the declared low voltage supply in the UK is 230 volts, but it is allowed to vary. The permitted range is plus 10% and minus 6%, which gives us a normal supply window from 216.2 volts up to 253 volts. The network operator's job is to keep the voltage at customers' supply terminals within those limits, except in exceptional circumstances. In the old street, that meant setting the transformer high enough so that the houses at the far end still stayed comfortably above the lower limit, even when everyone was using power. So the house next to the transformer might sit higher, while the house at the end of the road sat lower. Different homes, same street, different voltages. Now look at the same street today. The cables may be the same, the transformer may be the same, but the behavior has changed. And here's the thing, that street doesn't exist anymore. Some houses are no longer just taking power from the grid, they are generating it, storing it, and sometimes pushing it back. Solar inverters and battery systems do not export by whispering politely into the network. They have to raise their output slightly above the local voltage to push power back through the cable. So the voltage you see at home is no longer just about how far you live from the transformer. It is also shaped by what your neighbours are doing, how much load is on the street, who is cooking dinner, who is charging a car, who has solar exporting, and who has a battery system pushing energy back at the same time. The voltage profile becomes a moving landscape. In one moment, it slopes down from the transformer. In another, it can rise further along the feeder as local generation pushes back against the network. And that is the problem hiding in plain sight. The legal limits have not changed, but the street underneath it is no longer behaving like the street it was designed for. At this point, it is tempting to reach for the phrase smart grid and assume this is all being managed in real time. After all, we have smart meters, apps, connected devices, and half the country watching their solar output on a phone. So surely the local network must be adjusting itself minute by minute? No. Down at street level, the reality is much less futuristic. In many places, the local low-voltage network is still made from the same basic ingredients it has relied on for decades. Cables in the ground, overhead lines, joints, fuses, and a transformer feeding a group of properties. It may now have more monitoring around it, but it is not usually a magic self-healing grid with a voltage dial for every house. And that matters because we are asking that same local network to do far more than it was originally designed for. EV chargers and heat pumps can add large new loads, solar inverters and battery systems can push power back the other way. Sometimes that is helpful if one house is generating and a neighbour is using that power. The energy stays local and the network barely has to break a sweat. But the awkward moments happen when generation is high and local demand is low. On a warm, bright day, solar output can be strong, homes may not be using much power, and batteries may already be full. At that point, the exported energy has nowhere useful nearby to go, so it starts pushing further back through the network. That is when voltage rise becomes harder to manage. This is why network operators care about what gets connected. They want to know when an EV charger is installed and why solar battery storage and heat pumps may need to be notified to or approved by the DNO. It is not just red tape. One device might be fine. 10 devices on the same feeder can change the behavior of the whole street. So although the language around the energy transition sounds very smart, the street level challenge is still brutally physical. Same cables, same transformer, more load, more generation and power, no longer travelling in one neat direction. If you're an EV driver and you're facing this problem and need to charge your car right now, stay tuned for a hack. If you're an installer dealing with overvoltage complaints on EV chargers, hit subscribe, because what comes next is the bit that gets blamed on electricians, and it's not where most people think the problem sits. For most consumers, these voltage changes happen quietly in the background. Modern appliances, power supplies, and LED lighting are generally designed to tolerate a wide range of supply voltages, so the house just gets on with life. The kettle boils, the lights stay on, and nobody gives the local voltage a second thought. EV drivers, though, can become very aware of it. An EV charger may shut down a charging session and report an overvoltage event through the app. That is irritating enough in the evening. It is properly painful when you wake up, check the car, and discover it has not charged overnight, leaving you short of miles for work. At that point, the first call is often to the electrician who installed the charger. They may check the installation and say, this looks like a supply issue. You need to speak to the network operator. So the customer phones the DNO, mentions ESQCR, mentions 253 volts, and possibly begins the ancient ritual of desk thumping. But this is where the argument starts, because the charger may not simply be complaining about high voltage. It may be reacting to a safety requirement connected to a much rarer but much more serious network fault, an open pen conductor. And this is the problem that gets blamed on electricians. Pen faults are not happening on every street corner. The number usually quoted is around 400 reported open pen incidents a year across the UK. So we are dealing with a low frequency event. But when it does happen, the consequences can be serious. On most UK supplies, the neutral and protective earth are combined for part of the distribution network. That combined conductor is the pen conductor. Protective earth and neutral. If it is damaged or lost, metalwork that should be safely connected to earth can rise to a dangerous voltage. With an EV plugged in outside, that could include the vehicle body, so the wiring regulations take this seriously. Regulation 7.22.4.1.4.1 sets out ways an EV charging installation can provide protection where a PME earthing facility is used. But detecting an open pen fault is not beautifully simple. The symptoms can vary depending on local network conditions, load, imbalance between phases, and what else is happening on the street at the time. In other words, there is no little red flag that pops out of the pavement saying this is definitely a pen fault. That brings us to one of the simplest detection methods in the regulation. Clause D essentially uses voltage as the warning sign. If the line to neutral voltage is too high, above 253 volts, the charger treats that as a possible indicator of a pen problem and disconnects. It is a proxy, not proof, more of an electrical smoke alarm than a forensic investigation. Clause E then leaves room for other approaches, including more innovative methods of detecting dangerous conditions. But first we need to look more closely at Clause D, because this is where the overvoltage problem and the pen fault protection problem start tripping over each other. Lots of EV chargers on the market use the Clause D approach. And on the face of it, that seems perfectly sensible. After all, 253 volts is already the top of the normal UK voltage range. So if an EV charger sees the line voltage rise above 253 volts and disconnects within 5 seconds, as BS 7671 requires, you might think the case is closed. The charger has done its job, the supply is too high, phone the DNO. But the DNO is looking at the problem through a different lens. Network operators do not normally judge voltage compliance from a single momentary peak. They work to power quality standards such as EN 50160, which looks at voltage statistically over time. In simple terms, the voltage is assessed using 10-minute average values, usually over a 1-week monitoring period, rather than every brief spike or short-lived excursion. So now we have two clocks ticking at different speeds. The EV charger may see more than 253 volts and shut down within 5 seconds because that is how its open pen protection has been implemented. But the DNO may monitor the same supply and say across the required 10-minute averages, this network is still within limits. And that is the awkward gap. The charger is reacting like a safety device. The network operator is assessing voltage like a power quality issue. Same supply, same number, completely different rulebook. and that is not the only complication. The DNO is responsible for the voltage at the supply terminals, which in a typical domestic installation means around the service head and meter position. If the EV charger is mounted close to the meter cupboard, then the voltage at the charger may be almost the same as the voltage the DNO would measure. But not every charger is installed there. Some are fitted at the far end of a driveway in a detached garage, on an outbuilding, or fed from a distribution board some distance from the intake. And once you have a length of cable between the supply point and the charger, the voltage at one end of that cable is not always identical to the voltage at the other. Let's put some numbers on it. Imagine an EV charger installed in a detached garage. The supply comes from the house, runs down a sub-main and feeds a garage consumer unit. Then the owner adds solar PV to the garage roof with the inverter connected in the garage as well. When the car is charging, current flows from the house to the garage, so you would normally expect some voltage drop along that cable. But when the solar inverter is exporting, current flows the other way from the garage back towards the house and out to the grid. To make that happen, the inverter has to sit slightly above the voltage it is pushing into. So in the right conditions, the voltage in the garage could be 2 or 3 volts higher than the voltage at the supply point. The DNO might measure at the meter and see 251 volts. That is high, but still within the normal permitted range. Meanwhile, the EV charger in the garage is seeing 253 volts or just above, and because it is using the clause D method, it shuts down. And that shutdown can make the situation worse. A 7 kilowatt charger is a significant load. While it is charging, it is pulling current through the cable and helping to hold the local voltage down. But the moment the charger disconnects, that 7 kilowatt load disappears. The solar inverter may still be exporting, the sun is still shining, and the garage voltage can rise even further. So the charger tries to restart, sees the voltage is still too high and refuses to play. The very act of shutting down has removed one of the things that was helping to keep the voltage under control. The result is a frustrating little loop. Charger trips, load disappears, voltage rises, charger stays off. In some cases, it may not restart properly until solar output falls later in the day. From the driver's point of view, it looks like a supply problem. From the charger's point of view, it has simply followed its safety logic. But from the DNO's point of view, the voltage at the supply terminals is still within limits. So this is not necessarily a DNO problem. It may be a consequence of where the charger is connected, where the solar inverter is connected, and how voltage rises and falls inside the customer's own installation. That is the awkward bit. The number on the charger app may be real, but it may not be the same number the DNO is responsible for. Same property, same moment, 2 slightly different voltages, and a whole lot of finger pointing waiting to happen. So that is the theory, but what does it look like in practice? Because I have almost exactly the issue we have just been talking about. This EV charger was installed earlier this year, and it regularly trips out on high voltage. Sometimes it happens during the day, sometimes it happens in the middle of the night, sometimes it happens more than once. And when it does, the charger stops, the session ends, and you are left with that familiar EV owner lottery. Has the car actually charged, or has it spent the night sulking at the end of the cable? So time for a quick hack to solve the problem if you're facing this situation right now. What you need to do is introduce some load into the house, a sizable load like an electric shower. And what that does, because it draws so much power, it reduces the voltage and then probably gets to a level in which your EV charger can drop below 250 volts, switch on, start the charging process, and then switch the shower off. Not the most efficient approach, but it works. First, we need to understand what is going on here, because in this case, I think there may be a genuine high line voltage problem. This property is very close to the supply transformer, so I would expect the underlying voltage to be towards the higher end of the normal range. But the peaks I am seeing are often up around 257 volts. That is above the normal upper limit, and it is enough to cause a charger using the clause D method to shut down. At first glance, there does not appear to be much solar in the immediate area, so my suspicion is that the DNO needs to investigate the supply voltage properly. But there is a complication. They may point to my unregistered plug-in solar setup and ask whether that is contributing to the problem. I do not think it is. The symptoms do not appear to line up neatly with that being the cause, especially when trips happen in the middle of the night. But it does highlight a much bigger issue. Installers are increasingly finding that not all solar and battery installations are being properly notified to the DNO. Sometimes that is because the paperwork is slow, sometimes because the process is misunderstood, and sometimes because everyone assumes someone else has dealt with it. So you cannot simply look down a street, fail to spot a few obvious solar panels, and conclude there is no generation connected. There may be solar on rear roofs, there may be batteries inside garages, there may be systems connected that the DNO does not yet have properly mapped. And if the network operator does not know what is connected, it becomes much harder to understand why the voltage on that street is behaving the way it is. So yes, I am ready to start that process with the DNO and ask them to investigate, but there is another route through this problem, and it takes us back to Clause E. And this is the interesting bit, because Clause E is unusual. For the wiring regulations, it leaves the door open for innovation. It does not simply say, measure this 1 voltage and disconnect. It allows for other methods of protection, provided they can detect the dangerous condition and disconnect safely. For years, that idea was almost treated like a unicorn device, technically possible, talked about in the industry, but not something most installers expected to see in the real world. But the technology does exist. It is built into chargers made here in the UK by Myenergi, including the latest Zappi Glo, and it is now branded as ZapSafe to reflect its growing importance in this new electrical world. Instead of relying only on voltage as a proxy for an open pen fault, ZapSafe uses a layered approach. One of the key things it looks for is current flowing in the protective conductor to the vehicle. That is not the same as a normal RCD test, where the device is looking for an imbalance between line and neutral. In an open pen situation, the earth current can originate from outside the installation because the problem is out on the network, not necessarily inside the customer's wiring. ZapSafe then combines that earth current detection with voltage monitoring, but at levels above the normal ESQCR voltage limits. In other words, it is not treating every brief move above 253 volts as automatic proof of a pen fault. It is looking for a more complete pattern of danger before deciding to disconnect. That matters because it can make the charger far more stable in installations where the voltage is naturally high or where solar and battery systems are nudging the local voltage around. The charger still needs to protect against a dangerous open pen condition, but it is less likely to confuse a high, awkward network voltage with a genuine fault. So I decided to test this for myself. I've had this Myenergi Glo now plugged in on no load charging or waiting to charge the world's smallest EV now for over a month. And in that time, I haven't had a single notification to say that it's shut down because of a high voltage event. That also lines up with research from Myenergi. They looked at around 1,000 EV charger installations and found that only 6 experienced voltage-related trips, which they say is around 10 times lower than the rate seen with a purely voltage-based approach. So this is where Clause E starts to look much less like a unicorn and much more like a practical answer to a problem the network is only going to see more often. And this approach is now recognised within the new IET01 specification for open combined protective and neutral conductor detection devices, or OPDDs. In that document, this type of approach is referred to as a Mode 3 device, recognising that pen fault detection does not have to rely purely on voltage alone. I'll leave a link to the IET specification and to the Zappi Glo in the description. Of course, some viewers will have spotted the bigger question hanging over all of this. Earlier, we mentioned that the Energy Networks Association has submitted a controversial proposal to change the UK's voltage tolerance bands to more closely match the rest of Europe. That would mean a legal change to ESQCR. But would that actually fix the problems we have explored here? Would it stop EV chargers from tripping unnecessarily? Would it give DNOs more room to manage an increasingly messy low voltage network? Or would it simply make real voltage variation worse for customers already sitting at the edge of the network? That is the sticking plaster question. Are we solving the problem or just moving the legal goalposts? We will unpack that in the next video coming soon.